And now let's see the solution for test number 9. Okay. In test number 9, the question is that a particle having charge Q equal to plus 2 microcoulomb and mass 0.01 kilogram is connected to a string that is L equal to 1.5 meter long and tied to a pivot point P in the figure as in the figure. The particle, string, and pivot point all lie on a frictionless horizontal table. So this is a top view. Okay. The particle is released from rest when the string make an angle theta equal to 60 degrees with a uniform electric field of magnitude E equal to 300 volts per meter. This means the speed of the particle when the string is parallel to the electric field. Okay. So the situation is that we have a charged particle here, and this charged particle, we place this charged particle in the region with the magnetic field, with the electric field, and it's also tied with a string. Okay. We know that the electric field will exert electric force on the particle, and also we know that there is a tension in the string. So the result from the electric force and the tension will make the particle move in a part of a circle. Okay, this dashed line is a part of a circle. Okay, and to calculate the velocity of the particle here, we can use several methods to calculate this. We can calculate the electric force on the particle, and then calculate the acceleration along the path together with the tension, and then calculate the velocity here. But the simpler method, we can use the concept of force, the concept of work and the work energy or work kinetic energy theorem to solve this problem. This is simple because we know that the path of the particle is a part of a circle. We have the center as the point P, and the string lie in the radial direction. So it means that the tension on the string will lie in the radial direction, which means that the tension of the string will perpendicular to the path of the motion of the particle. And when the force that acts on an object is perpendicular to the path all the time, we know that the work done by the tension will equal to 0, right? So in this case, if we can calculate the work done by the electric force, we then can use the work kinetic energy theorem to calculate the velocity v. So first, how can we calculate the the work done by the electric force? Okay. The electric force, of course, is equal to QE, right? We place the charged particle with the charge Q in the region with the electric field E. So the electric force is QE, and the electric force will point in the same direction as the electric field. Okay. By definition, the work done by the electric force or in this case, here we will simply write that W is equal to integral of Fe dot ds, where ds is we may call it the differential part, or when we calculate the work, we divide the part of the particle into a very small segment, and each segment we define the vector ds along the path, and then we calculate the work done on each segment and sum up to get the total work done along the path, which is equal to the integral f ds, like this. If we substitute Fe as QE, so we have the work done equal to this term. Now, when we look at the vector ds, okay, we can see that we can dissolve this vector ds into two components. One component is parallel to the electric field, and one component will perpendicular to the electric field. By that, if we call the component that parallel to electric field ds parallel, and the component that perpendicular to the electric field ds perpendicular, so we have ds is equal to ds perpendicular plus ds parallel. Again, when we do this, we can see that we can write this term as this term as the integral of E dot ds perpendicular plus integral of E dot ds parallel. Okay. Again, since this ds is perpendicular to E, it means that dot product will always equal to 0. This is the reason that the work done by the tension is equal to 0, because the tension will perpendicular to the path of the motion of the particle all the time. So when we calculate the work done by the tension, which is equal to the tension dot ds, integral of tension dot ds, but tension dot ds is 0, so we have Wt, or work done by the tension, is 0. With the same reason, we can see that this component of the integral, that E dot ds perpendicular, will equal to 0, because this d perpendicular, ds perpendicular to E, so we have the term equal to 0. So we have only the second term left, that is the integral of E dot ds parallel. Now, since this component parallel to E, so we have that E dot ds parallel is equal to the product of the magnitude of E times the product of magnitude of E and ds, or E times ds parallel, right? Because we know that if you have two vectors, the dot product is equal to the product of the magnitude times the cos theta, where theta is the angle between those two vectors. Here, the theta is 0, right? Because E parallel to ds parallel, and cos 0 is equal to 1. So we have that this is the E times ds. And since E is a constant, because they say that the uniform electric field, okay, uniform means you have the same magnitude and the same direction everywhere. So we can put this E out of the integral sign here. So we have the integral of ds parallel. And what is the integral of ds parallel? You can see that this is very simple because the integral of ds parallel is just the summation of the ds parallel along the path of the particle. And you can see that for each segment, this is the ds parallel. Right? You can see that this is a ds parallel. This is a parallel component of the ds, the parallel component that the component that parallel to the electric field. So when you sum up these ds parallel, you will have the total length of the motion of the particle along the path that parallel to the electric field. Or it means that you project, if you look at this figure, if you project the initial position of the particle here and then the final position of the particle here, the integral of the ds parallel is equal to this distance, which we call here s. Okay? This is just a summation. We use no calculus here. We just use the symbol of calculus, but we perform nothing on the integral calculus here. We use the physical meaning of the integral. Okay? So we have that this integral is equal to S. So the work done by the electric force is equal to QES. Now, we can use the work kinetic energy theorem to calculate the velocity. The work kinetic energy theorem states that the work done on a particle or on an object must equal to the change of the kinetic energy, okay, which equal to the kinetic energy at the final point minus kinetic energy of the initial point. In this case, the particle is at rest, initially at rest. So the kinetic energy, the initial kinetic energy is equal to 0. The final kinetic energy is depend on the value of the velocity. This is the magnitude of the final velocity which we want to determine, right? So we have that K2 is equal to half of mv squared. Now we use the work kinetic energy theorem, and we have that the work done by the electric field is QES, and the change of the kinetic energy is the half of mv squared minus 0. Okay? And when we rearrange this relation, we get that V is equal to square root of 2QES m. We know the value of Q, E, and M, right? We have this value of Q, we have the value of M, and we have the value of E, like this. But what is the value of S? When we look at this figure, this is the value of S, which is equal to the difference of the length of the string and the length of the projection of the particle at the initial position, right? And you can see that this projection is equal to L cos theta, right? Because the total length of the string is L and this the angle theta here, so we have this equal to L cos theta. So the difference is S is the difference of the total length L and the projection which is L cos theta. So we have S equal to L minus L cos theta, or we can write this as L times 1 minus cos theta, right? So when we substitute this S into this formula, we have V is equal to square root of 2QEL 1 minus cos theta over M. And when you put all numerical value to this parameter, you will get that V is equal to 0.5 meter per second. I miss second here. Meter per second. So the answer is 0.3 meter per second.